Okay, looks like we're good. I came in after class and I was thinking, how do you actually get this camera to do anything? And I saw this remote over here, which has absolutely no instructions. And I just said, okay, I just played with it, and automatically the camera started going on. So everything's good. All right, so today what we'll do is we will finish the Steinberg tensor product theorem. So let me recall some of the ideas from last time. So G will be a reductive algebraic group. And again, we're thinking of it as a group scheme. The characteristic of the field is K. It's bigger than or equal to 0. Okay, so we have a Frobenius map from G to G. And then again, we iterate the Frobenius R times. So we have F to the R. And we look at, of course, that goes from G to G2. And we're looking at these kernels, which are the Frobenius kernels. Okay. Now, with the setup, if we have a representation rho, which goes from G to GLM, so this is a representation, then what we can do is we can twist the representation by the F to the R. So we get rho R, which goes from G to, again, GL of M twisted by R. And then rho R is just obtained by composing the Frobenius with the original representation. Right? And so the Frobenius kernel will act trivially on this representation. So this whole thing is going to be rho of R. Okay? And so let's see. So this is, so let's see. So M of R is corresponding rep.
Into the M to the R notation?
What is the what notation?
In the definition of rho upper R goes from D to GLM.
Yeah, so this is the composition of these two.
Like just about that in the line.
Here.
Yeah, so the M to the R.
Oh, I see. So basically, it should be just GLM, but I'm just emphasizing that you twist the representation over times.
I see. Okay.
Okay. It's the same vector space, but the action is twisted. And then GRX trivially on. Good. All right. Now, we know if we have simple G modules, they're indexed by dominant integral weights. And we have that the simple GR modules are indexed by the P to the R restricted weights. And last time what we proved is that when I take a simple G module and if I restrict it to GR, it's semi-simple. So L lambda, when I restrict it down to GR, this is semi-simple. And then if I assume that the weight is in the restricted region, the PDR restricted region for a G module, then it coincides with LR lambda. So L lambda, when restricted down to GR, is equal to LR lambda for lambda in the restricted region. And let me say where these results originated from. So these results go back to the 1960s. So this result, sort of just above this, is due to Curtis. And then what we're going to do is we're going to actually prove other results due to Robert Steinberg. Next. Any questions on this? All right, so we're in the midst of a proposition. Yeah. Proposition. So let lambda be an XRT and mu the dominant weight. Okay. So then I want to write the G module L lambda plus P to the R mu. This is isomorphic to L lambda tensor L mu, and I twist R, twist by R under the action of it after the R. So what this is saying is that you can sort of take a weight, which could be pretty high up, and then you can actually reduce it down to smaller weights, as long as you take twisted tensor products. So let's prove this. So before we prove this, I need to recall the Sockle formula for you. Okay. So let's recall the Sockle formula. So here M is a G module. Okay. And if I want to know what the GR Sockle is, then I think the direct sum over the restricted weights of L lambda tensor on GR. And I look at the number of times this L lambda appears in this. Okay, and this is an isomorphism of G modules. We're actually going to use this in the proof of this proposition. All right, so here we go. All right, so we're going to apply this to M being this module over here. So let M be equal to L lambda plus P to the R mu. Okay. Now, this is simple. So the Sockle over here So what's going to happen? So the only summand, there's only going to be one summand which is non-zero. Okay, so there is only one summand not equal to 0. Okay. So this means that this Hom here better not have, must be a simple module. So Hom GR lambda of M simple. So there exists a lambda twiddle such that M is going to be equal to L and the twiddle tensor L mu. Okay, so there's a lambda such that this is true. Actually, lambda in, let me just say, in XR T. Okay, so lambda has to be in XR T and a mu, which is dominant. So there's only one, can be one summand in here, so you can take one of these here, and this is going to be a twist of some simple module. Okay. And now what you do is you just compare the high weights. So now compare high weights. So that means that lambda plus PBR mu has to equal lambda twiddle plus PBR mu twiddle. And then sort of a uniqueness of p-adic expansions, these two have to be the same. All right. So now what we can do is we can apply this to obtain Steinberg's twisted tensor product formula. So here's the theorem. All right, so what you do is you do the following. So let lambda be some dominant weight. All right, so the way you think about lambda is in terms of, you write it out in terms of fundamental weights, and each of the coefficients are bigger than or equal to 0. And on each of the coefficients, you can sort of express things p-adically. Okay. So that means that I can write out lambda as lambda 0 plus lambda 1p plus lambda, let's see, what am I going to call it? Lambda m e to the m. And we'll do some examples in a second. So remember, the prime is fixed. Where each lambda j is in XRT. Okay, so the way you sort of can get this theorem, we'll see it just by iterating this process over and over. So then, when I take L lambda, that's going to be equal to L lambda 0 tensor L lambda 1 twisted ones tensor L lambda M twisted. Okay, and so this theorem actually just follows from this proposition, because what you do is you sort of first decompose lambda in terms of lambda 0 plus something times p, and then you take that something times P, and you decompose it again, and then you apply the theorem, and then you just keep on iterating this down. Okay. All right. Actually, we can do better than this. This is actually just in lambda 1. All right, so what does this say? It says that if I know all of the simple G1 modules, then I know all the simple G modules. So there's a corollary. In order to know the dimension of L lambda, or lambda in X of P, comma, enough to sort of know the dimensions of L1 lambda for, let me not mix lambdas together, the mu's, for mu in X1. Okay, so there are only finitely many. Let me just draw you a picture. So remember, this is the dominant region up here. And then you could just look at the restricted region, this X1 down over here. So what I'm saying is that if you know all the simple modules just here, okay, then you know all the simple modules everywhere in terms of the dimensions. So you just have to take, these twisted tensor products and then tensor product them together to get everything. So it's a pretty amazing theorem because you only need to know finitely many simple ones.
So in the extension in the theorem, do you not twist the L dot? Or L lambda on?
No, this one actually stays put. See, so whenever you have a P here, you have to twist by P, so forth and so on. Let me see, do we want to do the examples? No. We're going to talk more about this. General theory. Okay. Are there any questions on this? We're going to do examples later on.
Is this picture the same thing as before with like the two hyperplanes?
Yes. Yeah, so you're just taking the dominant region here. So remember, the irreducibles sort of appear as lattice points inside the dominant region. And this region here, you're only going up to P minus 1, P minus 1. Right, so everything's sort of below this, where the coefficients go up to P minus 1. And so if you know the irreducibles in the box here, you know the irreducibles everywhere. Okay. So let me already said this. All right, so let me continue on with this corollary and sort of give you some history behind what's going on. All right, so okay, so the simple modules. So the simple G1 modules are the same as the simple modules for the distribution algebra. And in this case, I think I mentioned before, this G1 corresponds to this restricted enveloping algebra. of the Lie algebra G. Okay, so it's a nice finite dimensional co-commutative Hopf algebra. Okay, so in 1980, George Lusztig provided a conjecture for the character of lambda, where lambda is in x1t. And this character is given in terms of the characters of the H0 lambdas. And the coefficients are given in terms of Cauchy-Lusztig polynomials. Okay. So via Cauchy-Lusztig polynomials. Now, the original bound was for p bigger than or equal to 2h minus 1. Right? And then Kato later on got it down to p bigger than h. So this conjecture was sort of around for p bigger than h for a long time. Okay, so the story kind of goes on, and H is the Coxeter effort.
Which part of the conjecture?
Sorry, which part is?
Which part is that conjecture?
That the character is given by these Cauchy-Lusztig polynomials. Okay. There's a sort of an explicit way to write them. I don't want to write out the correct form. And so this, what you do is you take the inner product of this row alpha check point 0 plus 1. So alpha 0 is a high short. All right, so let's fast forward a little bit. So this is the 1990s. People really wanted to compute the dimensions of the irreducible representations for algebraic groups and characteristics P. And so, so this is lots of people. So it turns out that you can get sort of equivalence. I shouldn't say quite equivalence, but you can actually get a correspondence between simple modules between the restricted enveloping algebra, and here this is a quantum group. Okay. And then there's an equivalence of categories with modules for the affine Lie algebra. Okay. Now, this equivalence is due to Cauchy-Lusztig. Okay, it's actually an equivalence of tensor categories. And Kashiwara and Tanasaki proved this formula over here in the affine Lie algebra category. So let me state that. The Lusztig conjecture. All right, so for the quantum group, everything was fine. Now, here's where issues come in. So Anderson, Janssen, Serval actually showed that the dimensions of the characters match up as long as P is sufficiently large. So So they actually proved it for P very, very low. And there was no effective lower bound at the time. So in principle, for very, very large primes, they didn't know how big, this conjecture turned out to be true. All right, so let me go forward a little bit. Maybe it helps to actually have lived through all this. I shouldn't. I remember when people were actually working on this. Okay, so now we go to the 2000s. And Liebig actually showed that what sort of lower bounds you have. So either Liebig show LC conjecture holds for P bigger than, let's say, N, and N is some effective lower bound. And these effective lower bounds are just astronomical, in the millions. And for type A, for example, the bound depended on N for sure. All right. Okay, so the final part of the story is in 2013. I was actually at this conference when this result was announced. So this is pretty exciting. So Jordy Williamson showed that the Lusztig conjecture is false. Okay, so actually this conjecture is stated is false, and he produced infinitely many counterexamples. And he also showed that this bound over here does not depend linearly on the rank. So that means that this P has to be very, very large. You can't. There's no linear bound. Like it's not like 4h minus 1 or 5h minus 1. Okay. Are there any questions on this? So it's still an open question. What the character is for the irreducible representations for the algebraic. Still an open question.
I guess this shows they're not given by the KL polynomials, but is there any suspicion of where else they might come from?
Yeah, so that's a really good question. So Jordy and other people have been looking at characters for tilting modules. And the conjectures that the tilting module characters are given by what are called P rationalistic polynomials. Okay, and they're very, very hard to compute. These cardinalistic polynomials you can actually compute. They're computable. But the P cardinalistic polynomials are almost like sort of non-computable in some sense. But so you have a conjecture for the characters of the tilting modules. And then if you know whether Dawkins' tilting module conjecture is true, it's true for P bigger than 2h minus 1. Then you can translate that to the characters for the irreducibles. Okay. So For a 2H minus 1, the answer is yes. There is a character formula involving P canonical basis or P customalistic polynomials. Okay. If we have time in the class, I'll talk about Donkin's tilting module conjecture. We actually found a counterexample of that last year. So I found one with Van Mulkel and so much of this. Okay. All right, so the next thing I'd like to do is I'd like to do some examples. We'll just stick with SL2.
For the tilting modules, so you expect there's some kind of similar intersection homology with them, or?
No, I don't think so. There's this kind of parity sheet business, but I don't. Yeah, I don't know if there is or not. I'm not the right person to ask. Okay. So let's do some examples here. So let's stick with G equals SL2 for a second. Now in this case, so let's see what the restricted region looks like. So the restricted region has a weight 0, 1, 2, up to P minus 1. So remember, the dimension of the torus is one dimensional. So that's what the restricted weights look like. Now I mentioned before that the L lambda is, well, let me be careful. If I take H0 lambda, this is going to be the symmetric power. So let me see, 0, yeah, symmetric power on P. Okay. So remember, here, lambda is the dominant weight. And dominant weights are just 0, 1, 2, and they can kind of go on forever. Okay. Now we know that L lambda sits inside of H0 lambda. Submodule. And so what you can do is you can do a calculation involving these symmetric powers of the natural representation. And then there's a theorem that says the following. So it turns out that L lambda is equal to H0 lambda, or lambda, which is restricted. So as long as you're sort of down low enough, then your L lambda is irreducible, your H0 lambda is irreducible. Okay, so maybe that's 1, and theorem 2 is that the dimension of L lambda is equal to lambda plus 1, or lambda n. Okay. Very good. Now let's actually specialize a prime. Okay, so let's say p is equal to 3. Okay. And so now let's look at the restricted weights. So the dimension of L0 is by this theorem 1. The dimension of L1 is 2. And the dimension of L2 is equal to 3. Okay. All right, so remember, this is the natural representation. And this turns out to be adjoint. This will be algebra, which is 3-dimensional. Okay. All right, so now what's the dimension of L4? Anyone want to see how to do this?
So you want to apply the tensor product formula.
Yes.
Let's see, what is it going to be?
So how do you write it in terms of a 3 out of 10? Yeah, someone said it. All right. 1 plus 1 times 3. Okay. So by Steinberg's tensor product formula, L4 is L1 tensor L1. How many times do I have to twist it?
Just one.
Just once.
Magic.
Oh,
It's like magic.
it is. It's great. So what's the dimension here of L4? Four. Right? It's 2. This one has dimension 2 times 2. And that's 4. Okay. Yeah, and you could see what to do. So I'll just do one more. Okay. I don't know. Maybe we should something more exciting. Let's do 7. All right.
Does the twisting change the dimension at all?
No, it doesn't. The vector space is still the same. The action is just different. It doesn't change the dimension. Okay, so let's do 7. So maybe this is not. So this is what 1 plus 2 times 3, right? You okay with that? So then L7 is equal to L1 tensor L2, again twisted 1 time. Okay, so the dimension here of L7 is what? It's 2 on this one, and it's 3 on this one. So it has dimension 6. Okay, any questions on this? Let's see. Okay, good. All right, so now I'm just trying to think. Maybe I should go up to 5. Okay, so we have a little time. Let me go up to 5. And then I'm going to illustrate another point equals. All right, so let's do p equals 5. So I'm going to write out the same type of things. So if I do, let me just do this one. So this is going to be one-dimensional. Dimension of L1 is 2. Dimension of L2 3. Dimension of L4 3. Sorry, it's 4, and dimension of L4 is 5 dimensional. All right, so I just did something like this. So now what I want to do is I want to look at H0 of 5. So I'm going to consider H0 of 5 here. Now, what do we know about H05? Well, first of all, L5 is a submodule of H05. Okay, it's basically the socle. Right? Now, what is the character of H05? Well, let's think about this. So this comes from like Lie algebra representations, right? So, you know, you have 5 as the highest weight here, and then the weights go down by 2, right? So 3, 1, minus 1, minus 3. Okay, so the character looks like E of 5 plus E of 3 plus, well, let me just write it down. I'll be All right. How do we find the composition factors of H0 plot? I know the character of this one. What do you think I should do next? Let's see how to do this. Let me think about this for a second. So what do you, if I take L of 5, can I actually compute the character of that?
I mean,
Or do I know the dimension of L of 5? Yes or no? How do you come to be at the dimension of L of 5 here?
Dimension just 1 here?
Dimension is 1. Well, I mean, to compute the dimension, so how do I, so I want to know something about L of 5 here. I know it's a submodule inside of it.
Here, one of these like tensor product formulas for L.
Yeah, so I just write, I use Steinberg's tensor product formula, right? So Steinberg's tensor product formula. So 5 is what, 1 times 5, right? So L of 5 is L of 1 twisted once. Okay. Do I know the character of L of 5 now? What do you think about this? Do I know the character of L of 1?
it's simple, right?
Yeah. Okay, so the character here, L of 1, well, it's just going to be E1 plus E minus 1. It's the natural representation. Right? The weight spaces are 1 and minus 1. Okay? So when I twist, I just multiply by P. So the character of L of 5 equals the character of L of 1 twisted, and that's going to be e to the P. Twisting by P, so that twists the weight space. The action is twisted, and I multiply by P. That's what the Frobenius does. Okay, so P here is 5. So let me just put 5. All right.
Is it just a coincidence here? This is like a hyperbolic sine or cosine or something.
I don't know about that, so. Okay, so the point is now, I want to compute the composition factors out of here. All right. So now what should I do? There's one composition factor inside of here. So now what should I do?
Should quotient out.
I should what?
Should be quotient out.
Yeah, so when I take that thing out, so what happens to the character? What do I do to the characters? Subtract. Very good. So I want to look at the character of H05 minus the character of L05. Okay, so we just subtract out this from this, and I have E3 plus E1 plus E minus 1 plus E minus 3. Okay. So which composition factor is going to appear inside of here? L3. Okay. Now, if I look at the character of L3, now this is down in the restricted region, right? So this is an H0. So I have 3, 1, minus 1, and 3. That's good news, right? So we cut everything out. So this is E of 3 plus E of 1 plus E of minus 3. E of 1 plus E of 3. All right. So what this shows is that with the knowledge of the characters of the irreducible representations, I know how to compute the characters of the H0s. I mean, I know how to calculate the, I know the characters of the H0s, and therefore I know the composition factors. So that's what the moral of the story is. But I wanted to work through an example with you on this. So, composition factors of H05 are L5 and L3. All right, so let me kind of draw a picture for you. So this is a number line. So I'm going to draw it vertically here. Okay. And so what I'll do is I'll label the restricted region in green. So there's 0, there's 1, there's 2, there's 3, and there's 4. Okay. So these are the weights in the restricted region, right? And what I want to do is I want to put a line here. So I'm thinking to have a line sort of, on like P minus 1 and 2P minus 1 and so forth. And then here's 5, here's 6, here's 7. Okay. And so notice that when I take H05 here, okay, then if I reflect across this line, I get 3. Okay. All right. So reflecting across the line corresponds to the action of the affine vowel. So these reflections correspond to WP, which is the affine. Okay. All right, so now suppose I'm up at 7. So now I want you to guess what the composition factor. So you know that L is 7 is a composition factor of H07. So what do you think the other composition factor is going to be? Yeah, so let's see. 1, 2, 3, 1, 2, 3. This will actually go down to that one over here. Okay. And this phenomenon, in terms of obtaining possible composition factors via the affine Baugh group, is called strong linkage. Let me just say this. So, a strong linkage, which we'll go over later on, principle provides possible composition factors of H0 lambda. Okay, so for example, this 2 is not strongly linked to 7. So L2 will never be a composition factor of H07. Okay. So it gives you the possible ones. Not every one may occur. Okay. But they have to be in the same orbit under the action of the affine Baugh group. All right. Let's see. Okay, so another thing that we did was just apply this again. So now we sort of know something about this. Okay. So we calculated the composition factors of H05. So what's the structure? So the structure is L5 sort of sits at the bottom, and it's in the socle, and there's a non-trivial extension between those two modules. And what we showed a while ago is that all extensions between simple modules occur in the second layer. Right? So this shows that X1 of G of L5 with L3 is one-dimensional, just isomorphic to the field. Okay, so by knowing the structures of the H0s, you actually know what the extension information is, at least for X1. All right, good. Now, this picture extends more. So let me show you actually a little more complicated picture. Are there any questions on how to do this? We'll do more examples later on when we do character computations, but this really is a kind of a hands-on thing to actually know the weight spaces, and then you keep on subtracting off various weight spaces, and then you just sort of pick off the character that way.
So in that example, we're using SL2 theory pretty heavily. We're using SL2 theory, right, to get those weights. Like in the other types,
yes.
You need to use the character formula or something to get H0.
Yeah, that's correct. So the idea is for H0 lambda, you know the character by what's called Weyl's character formula. Okay, so that's okay. The problem is we don't know the characters of the irreducible representations in the restricted region. If we knew that information, we would be able to get the composition factors. Okay, Now I'm going to preview a little bit. So this is minus rho here in that case. And so if you want to do the A2 picture, what you do is you shift the origin down to minus rho in that case. Okay? And in this situation, here's the kind of the restricted region. So here's P minus 1, P minus 1. And if you want to look at the action of the affine file group, and you have things like that. Okay. So for example, so this is like 0, 0, and this is P minus 2, P minus 2. Okay. So it turns out that if you take this H0 here, it will have two factors. You'll have this factor here, and then I'll have this one factor. You can actually prove that using what's called the translation principle. So you have this action of the affine file group, and then you have things which go like this, like this. You can sort of see what's going on. Okay, so you have reflections across these affine hyperplanes, in addition to the ones that you just get for the ordinary file. And so this is a much more complicated picture than in category O, for example, if you take in the category O class. And that's why, for example, the category O conjecture for the Lusztig theory is actually proved, but in this case, it's still. Okay, so let me stop here.
Moving between the triangles that is the affine boundary.
Yeah. So were you able to hear okay, Emily?
Yes, I could. Thank you.
Okay, that's good. Everyone have a good weekend.